So there's one more coverage analysis we have not covered, which is the one that you would need if you would do level A code. And it's called Modified Condition Decision Coverage, or MCDC. So if you look at the definition of MCDC, it means that every decision in the program has taken all possible outcomes, and every condition in the program has taken all possible outcomes. And this, we saw this before in a condition decision coverage. But in addition, we have that each condition has been shown to affect the outcome of the decision independently. Okay? So it means if I can show that by just changing one of the conditions, I can change the output of the decision. I need to show this for each of the conditions. Of course, you can foresee one problem with it if you would have this particular decision structure. If you have A or B and A or C, I cannot change I cannot change A from true to false, false to true, while keeping B, A, and C constantly unchanged, because of course these A's are coupled. And we'll talk about this. We're going to solve this by a thing called masking MCDC, and we'll talk about that in a little bit. Alright, so if you look at unique cause MCDC, and I suppose I'm taking as example this particular decision, A or B and C or D, I could set up all possible combinations of A or B. So in this case, you see there's 4 conditions, so all possible combinations with 50 to the power 4 is 16 different test cases. And you see in these test cases, they range from A, B, C, D being false and true. Now, so what you can see, if I look at condition A, I can find 2 test cases, in this case 2 and 10, that in which case B, C, and D stay constant at false, false, true, but just changing A, I can change the output Z. So in this case, the combination of test case 2 and test case 10 can be used to show independence for A. So it can be shown that I can change the outcome by just changing A for these test cases. Okay? So, and you see the same thing is true for test case 3 and 11, because 3 means false, true, false, 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 true, false, true. So you see, and that explains this. 2 is combined with 10, 3 would be combined with 11, 4 would be combined with 12. But you see 5, would be true, false, false, and then of course would be true, false, false. But if by going from false to true, it would not change the outcome. So hence there's nothing in this item. Similarly, you can also say I'm taking out this 2, and if I just focus, for example, on now B, you see this is false, false, true, and B is false. If I look at 6, B becomes true, but A remains false, C remains false, and D remains true. But just by changing B, it causes the output to toggle to true. So it means that test case 2 and 6 combined show independent change of the outcome based on B. So you can do this for the whole table. If you see this, that means that test pairs 210, 311, and 412 show independent effect of A on outcome Z. At the same time, 2 and 6, 3 and 7, and 4 and 8 show independent effect of B. 5 and 7, 9 and 11, and 13 and 15 show independent effect of C. And then finally 5, 6, 9, 10, 13 show independent effect of D. So out of this I can combine a set of test cases. So for example, if we take 2, 5, 6, 7, and 10, then we'll have 2 and 10, so it covers A. 2 and 6, that covers B. 5 and 7, that covers C, and 5 and 6 covers D. So these 5 test cases will be sufficient to do unique cause MCDC. Now, Typically, rule of thumb for any input conditions there you will need n plus 1. So in this case 4 input conditions, A, B, C, D. It means 4 plus 1 equals you need 5 test cases. And all these pairs that you see here are often referred to as the independence pairs. Okay, now let's look at masking MCDC. Let's take our test cases that we saw in this case. I'll look 2, 5, 6, 7, and 10. So 2, 5, 6, 7, and 10. So in test case 2 it was false, 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 true. You can see test case 2, false, 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 true. Test case 5 was false, true, false, false. Test case 5 was false, true, false, false. Then test case 6, false, true, false, true. 6, false, true, false, true. And then test case and etc. etc. Well, if you look this, if you take this Boolean expression, this decision, and write it down as a kind of a digital block diagram, I can say, well, I'll break it down to two proxy variables, A or B, given by this OR gate that takes A or B, and C or D. And then I'll take the output of the two OR gates and AND those two together. So in other words, this digital logic is really, these digital gates represent the digital gates given in a decision. So it's a schematic, a digital logic schematic diagram. Now, okay, let's look at 5. Yeah, if you look at 5 and you say, oops, in 5, A or B is unobservable at Z because of the false output of C or D. Yeah? So think about it. If you look at test case 5, you see the output of test case 5 results in the output of this OR gate to be false. This causes the output of the AND gate to always be false. It doesn't matter if this is true or false. It doesn't matter what this is. The output is always going to be false. So this means that there is masking going on. It doesn't matter what A or B does in this particular case. Yeah? So C or D is unobservable at Z because of the false output of A or B in test case 2. In test case 2, both are false. That causes this to be false. That causes the output of the AND gate to be false regardless of what the other input is. So it means that C or D is unobservable. This can be either false or true. It doesn't matter what C or D are. And this effect is called masking. So there is another way you can do this called masking MCDC. Instead of saying that a condition is shown to independently affect the decision's outcome by varying just that condition while holding the other ones fixed, in masking MCDC, you allow more than one input condition to change in an independence pair as long as the condition of interest is the only condition that affects the value of the decision outcome. Remember, on this case, in pair 5, it doesn't matter what these are, they don't affect the outcome if C or D is F. So in this particular test case, A or B would not affect the outcome ever. Okay, so let's look at that. We take our same decision again and say, well, you take test case 2, for example. Test case 2 is false, false. So if it's false, false, the output of the OR gate is false, and it doesn't matter what C or D are. So in this case, I ignore C or D. Yeah? This doesn't matter. It can be true, false. The outcome is always going to be false. However, this becomes true, then this one becomes true as well. See, these really don't matter. This is nice, because now rather than having just one possible combination, I have 3 possible combinations. These 3, I added 3 and 4 to it, because 3 and 4 don't matter. True and false still gives you true here, and it really doesn't matter what they are. So this now means that output pair case 2 could be paired with either 10, 11, or 12. And then you could actually just do this also by just rewriting this equation as A or B and Y. So masking MCDC allows you more independent pairs per condition than in unique cause. Now, this is perfect when you have coupled conditions. If there's conditions in the next coupled conditions, and this is the one where we have, for example, A or B and A or D. Okay, I was going to give you an example of that, but before I do that, let's just look real quickly at some test case conditions here. So let's look at this low-level requirement, and now say based on this low-level requirement, somebody came up with the following 3 test cases. It says first case, the connect weight on wheels, input too low, which means this will be false, and the airspeed to 220, and of course the rollout upper limit is 95. So then what you see is that this will be false, and this will be false as well. So this is really false, false. In this case, connect weight on wheels too high would be true, would be 1. And this would be 10 knots, so this would be true as well, so it would be true, true. So we have false, false, true, true, and then in this particular case, this would be true, false. So what you see here is I kind of translated, I wrote my test cases as actual descriptions rather than as trues and false, but they can be interpreted as true and false. This would be true, true, sorry, false, false, true, 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 false. Okay, so if you code it like this, you can say with these coding conditions, I could have, I can check my, if you look at decision coverage, if I would look at this, then true, true, false, true should cover it. Condition coverage, true, false, false, true would cover it. But what you see, you can derive that pretty easily. But if you look at MCDC, you need to have true, true, false, true, true, false. So you had false, false, true, 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 false. This is not satisfying MCDC. So I would have to change so these 3 conditions do not satisfy my MCDC case. So what I would have to change it. I would have to change this condition to false true, this condition to false true for it to meet MCDC. Okay? So I can do that by saying, for example, setting the airspeed to 10 knots. In this case, these 3 test conditions are sufficient to show MCDC. Okay, so we started talking a little bit about masking MCDC, and I kind of got a little off the page there when I started talking about masking earlier, but let's look at it. Suppose we have this particular implemented requirement here, if dark sensor and nighttime, or not dark sensor and manual input. Well, this is of course pseudocode. If you look at this, this would be really, if you look at the dark sensor discrete as A, not dark sensor and not A, nighttime as B, and manual input as C, then this really would look like the following Boolean expression, A and B, or not A and C. You see there's strong coupling going on because of this dark sensor discrete being on both sides. So what I could do here, I could use the truth table for masking MCDC to cover myself. Yeah. And in that case, I would have test cases 5, 15, 12, and 6. Okay. So I would actually perform again what I had before. For example, I take test case 2, but what I realize is that in test case 2, by masking, rather than having just test case 2, I can actually have test case 2, 6, and 10 representing the same masking MCDC conditions. This gives me a little bit more choice in cases, And now I can also get rid of the cases in which this condition A and that condition A are different. For example, this one it's hard to do because here A is true, here A is false. This one works, A is false and A is false, so I can get rid of these completely.